Okay, hello, this is Max. We're working on fall 2013 midterm 2 question 3C. It's asking us to define parts. So anyway, I'll just read this question. The function fold tree takes a 3-argument function, a 0 value, and a tree. It returns the value of replacing tree with the function and empty branches with the 0 value. For each of size reverse repeated, complete the inner function f. Each f cannot be recursive. Okay, so like all questions, we have to decipher what this question is actually asking. This one's a little more complicated than a lot of other ones, but we can sort of look at our doc tests for some guidance. Okay, let's start by making a tree. Got a tree that has 5. Also, one note. This is a fall 2013 midterm, and we had a slightly different definition of tree here. So if you're looking at this in spring 2015, then, or later, we might have changed things. We're looking at this class tree here. So the class tree, it's going to take some left and a right branch, some left and right values, and an entry value. And this is very similar to our binary tree example that we have now. So it only has 2 branches. It doesn't have a list of branches. Just something to think about. Okay. So here, a branch is considered none if it has sort of none as our left branch. This is not a valid tree. This is just something that signifies that there's no value in the left branch. And then the tree, the value 3, and then here we have 2. Okay, so we've built our tree in our first doc test, and now we define some function, which we can sort of think of as sum. It's going to sum up all of the values at each of these entries. And when we apply it to here, this is going to do the recursion for us. You can sort of see here, it's going to apply this lambda function to tree.entry, and then the results of calling fold tree fn0 tree.left and fn0 tree.right. So this is a little non-intuitive initially, because when we teach you trees, we tell you, okay, you need to implement all the recursion, and here in this problem, we're implementing the recursion for you. You just need to think about how you're gonna, what function you're gonna put in for this fn right here. So when we look at this, what happens is we replace all of our none values with 0. So each of the things that don't have any children, that is gonna be replaced with the value 0. And then we're gonna sum all of these elements up. And so what we're gonna get is 13. And you can see here, 13 is the total sum of each tree.entry in this tree. Okay, great. So that's the first thing. We sort of now have a better idea of what this question is actually asking us to do. And now we can sort of approach it. Okay, so return, first thing we need to implement is size. Return the number of trees contained in tree. Size tree, 3, 5, same example we have here. Well, this is sort of, so number of trees contained in tree. Well, what's a tree contained in a tree? This is just any valid node, right? Because this is going to be the root. 5 is going to be the root of some tree. 3 is the root of another tree. Anything that isn't none here is the root of some tree. So we're gonna, this is sort of asking us, okay, how many nodes do we have in this tree that are valid nodes, right? This none is not a valid node. Okay, so what can we do here? Well, we know entry is a valid node. So if we're actually calling this, we're not going to call this on the 0 function. So we know that we can just return, we can at the very least return 1. And then we want to return the size of each of our subtrees, right? So we say this is going to be at least 1, and then we want to return the size of both of our subtrees. And both of our subtrees here are defined as the recursive calls of size to our left branch and our right branch, which is sort of what we can see here, right? So this is a recursive call. We just replace this fn with size onto our left branch and our right tree. So our left branch and our right branch, right? So if I say 1 plus left plus right, what I'm going to get is, as I look down this tree, I'm going to get 1 for the node, plus a call to size on this branch, on this tree down here, which is 2. Right, so this tree has no children, and so our left and our right are not going to get called at all, because that is going to get replaced with 0. And so we're going to get, this is going to return 1. And then this tree here is going to return 1 for this, 0 for this, and another 1 for this. And so we're going to get 4. Okay. So that's size. 1 plus left plus right. because left and right are going to be replaced with 0 if it's an empty tree. Okay, so that's that first one. Now reverse. Return a new tree. Okay, hint, new tree. We're going to need to use a tree constructor. Swapping all left and right branches of tree. So that means if we have something like 3, 5, 3, 2, we want to swap our left and right branches, and we're going to get something that looks like 3, 2, 5, 3, none. Right, so you can see here, these branches were swapped. Up here, these two branches were swapped. Okay. Okay, so let's just start by, I'm going to say return. We need to make a new tree, right? Our entry is going to stay the same because we're not swapping the value of our entry. And then, well, this seems like there's really only one thing left to do. We need to swap our right and our left. Okay, why does this make sense? So this left is going to be our swapped left tree, right? Because we're doing recursion up here. This is going to be a swapped left tree. So this is going to get swapped so that it's 5, 3, none, right? And now, so we want to actually put this tree into our right branch, and then this tree doesn't have anything, but we're going to put our whatever our right branch was into our left branch, right? So the tree constructor is going to take a self and an entry and a left and then a right, and so we're putting our right branch into our left slot and our left branch into our right slot. Okay. Okay. So now repeated here is going to return how many times the root entry of tree, this tree here, appears in tree, okay? So how many times is the root entry of tree in our tree? So this f is going to get called for every subtree, okay? And so we're going to say these left and right functions. We have to remember these are recursive calls to repeated. So how can we, all right, so left and right. So first, what do we want to do? We want to check to see whether or not, and then this entry is going to be the entry of the tree we're currently looking at. So first we're going to inspect this tree here, then we're going to inspect our subtrees right here. So when we make this call, our entry is going to be 2, but we've kept track of what our root entry of this whole tree is when we called repeated tree, right? Because tree is passed in right here, so we can check count. First is equal to 0, and then if count, let's say one more time, if entry equals tree.entry, so if the tree we're currently looking at, its entry is equal to the tree that this function was initially called with, this entry, then we're going to say count is equal to 1, because then we have at least 1. And now we're going to say return count plus our recursive calls to left and right, which is how this function is defined. So the key in this function is to have looked at this and realized that left and right are recursive calls to our left and our right branches given this function. So we pass in this function and pass in our left and our right branches. Okay, this is confusing. If you have questions about this, please feel free to post on Piazza or YouTube, and we'll try and get any questions answered. Okay, thanks for watching.